I think we should be back now. Man in the High Castle, I heard good things about on Netflix. So I think that this bit was pretty clear. We talked about arrays last week. This ampersand for getting the address, star for dereferencing. Strings will break many things about your day. The only thing that's worse is your webcam crashing. And there was last week this bit of slide karaoke. You might be able to tell that I hadn't really prepared that bit and it were some other people's slides. So we're going to do a bit of a do-over of that now. So this week, the stack, and why we're going to go over this again is because the stack is really important. You really need to have a good understanding of how the stack works to be able to execute the attacks that we're going to be doing later in this course. And knowing what the return address is in particular is going to be very helpful. Local variables, how can we manage those efficiently? For example, we have here that some function is being called by the main function, and then there is this, they both have their own copies of local variables that need to have some space assigned to them, and that's 100 bytes for this sum function thing. Main has these 4 integers. They need to be put somewhere, and how do we do that efficiently and ideally with as few overhead as possible? So local variables are local not only to the function, but also to the function call. If you call a function multiple times, each one has its own copy of the state. That holds especially if you're calling something recursively, because otherwise you would run into horrible messes. And another property of local variables is that they are only present, or they only need to be present during the function call. So we could investigate several options for doing this if we were to, say, build a compiler. So we could, for example, turn every variable into a global variable, but then you have all sorts of isolation issues if you have to make more than one copy, because you need to have each function call have its own version of the local variables. You need to fully trace the entire call graph to make sure that there's no recursion or something, or that the function is being called multiple times throughout this function call tree, and then also create copies, and it costs extra space. It's also not always possible because programs might do stuff differently based on the input, and then it quickly becomes an undecidable problem. Clearly, this is not an option. Another option might be doing active management, like how we manage heap variables. But then you have this overhead of having code being executed before every function call can really start, because then you need to get space, and you have all these segments of space, and it might be fragmented in some way, and then you need to figure out, okay, I can put some stuff here and some stuff there. It's a big mess. So you also then need to make sure, again, that you don't have collisions between function calls, so you need to do all of these checks per each function call. And then also clean up all of this memory, mark it as available for other functions again, etc. This is a bit messy, but you might say, why do we accept this mess for heap variables? Well, those are usually somewhat longer lived, and they can be shared between different functions or different threads even, and that is there possible. An acceptable loss, and also we don't really know how to do better there, but for local variables we can definitely do better, and that is by realizing that functions are like a ladder. You can go up the ladder by calling another function and another function and another function, or we can go down the ladder when we step down. And when we return from functions, we do steps down of this ladder, and then going sideways is not possible. You cannot jump from one ladder to another ladder. Multi-threading makes this story a little bit complicated, but then you could say there are multiple ladders but yeah. At the bottom of the ladder, we put this main function. Or we could say that we put it there. And this behavior of going up and going down again, we use it to manage the local variables on the stack. And we do that by pushing the variables on top of it, and whenever we call another function, it also just pushes everything on top of it again. And then when you're done, you can just take that top bit, throw it away, and it's gone. And the only thing that you then need to keep track of is where is the top of this stack. So we have these stack frames and the stack pointer. The stack pointer is the piece of information that keeps track of where we are on the stack, and the stack frame is the space used by a certain function call. So we have this call, we're somewhere in the main function, and main has allocated this bit of stack space, and the stack pointer is pointed at the end of the stack. Note that the stack starts at the high addresses all the way at the top, so it grows downwards towards 0. Then we start to call func here with the arguments 42 and 23. What we then do is we get the stack frame of func, and then the stack pointer is decreased, so func has its space to put the local variables that were here. And then when it's done again, we increase the stack pointer again to go back to where it was. Zooming into this stack frame, we can see the stack here before we call func. What will happen is that the caller will first put the arguments for func on the stack, and then put the return address there. And the return address is the place in the memory where the code is, of the place where you were before you started jumping towards this function. And that address is then where you want to go back to execute the rest of the main function once you're done with func. Then there's this other thing, and then you increase the stack pointer by enough for the callee to push its local variables onto the stack. So, spoiler alert, the frame pointer, that points to the end of the stack frame, namely that the frame pointer and the stack pointer between those two items are the local variables. Why can you use that? Well, for example, you might remember, oh yeah, that was the second byte that I pushed to the stack. Well, then you can take the frame pointer, add 1, and then you'll find the this variable. Whereas if you would do that with the stack pointer, you need to do a little more bookkeeping, because then you also need to keep track of, okay, how many things have I pushed since? That is still very much possible, which is why you might leave it out on AMD64. That will give you an extra register. You can just tell the compiler to leave out the frame pointer, and then your program might run faster. It's being stored on the stack so that when you return to calling main, this thing is popped, this address moves up, or this arrow moves back up to this thing, and then you pop the when you pop all of these things off, then you will again have that the frame pointer points at this point and the stack pointer points here. So yeah, having this extra register really speeds up things. You only have 16 registers on AMD64, so having one extra or having one less taken up by stupid admin stuff is very helpful to make stuff run faster. So summarizing all of the sorts of things that the stack is also used for is passing function arguments, keeping track of this return address, storing the return value on some platforms, and managing this frame pointer. And for these function arguments, it's important that on AMD64, for reasons of speed, the first few are passed by registers, because when you have to go through memory, that is really very slow. So the less you need to do that, the quicker your program will run. And how they came up with these specific values, I have no idea. They probably had some idea why this was a smart number to pick. I I'm sure Microsoft has enough smart people working for them that they decided that 4 was a good value. The rest of the world, so OS X, BSD, Unix, Linux, etc., chose 6. Probably also had very good reasons for that, but don't ask me. This return value is also not something that you will find on the stack on AMD64 because it's also being passed via a register, again for reasons of speed. So back to Stack Overflow. Running out of stack space, you either had limits by how much RAM you just have. If you have 16 gigs, it's hard to use more than 60 gigs of stack space. Other limits might be set by the operating system, as very nicely demonstrated by myself earlier. These limits you set to make sure that when you write a program that misbehaves, such as my function that very quickly exhausted my RAM when I said you limit unlimited. That's the kind of stuff that why the operating system enforces these limits. Often a large amount of stack usage is an indicator of poor programming. Stack overflow can be caused by recursion or infinite recursion, too large local vars, or and it doesn't necessarily always have to be infinite recursion, because recursion, just going for 1,000 layers might also already exhaust the stack. You saw that there was 8 kilobytes of stack space by default. If you go 8 layers deep and in each layer you allocate 1 kilobyte of stack space, then you will already, or no, it was 8 megabytes of stack space. So if you go 8,000 layers and allocate a kilobyte in each one of them, you will already run out of stack space. Stack variables are not auto-initialized, so what you will read there if you haven't initialized them is whatever garbage was left there by a previous function. And that is, of course, undefined behavior, but you could use that to figure out what another function did if you write a careful piece of code. Another thing that stack does is mixing program data and control data, and that is why if you overwrite your buffers, you could overwrite a frame pointer or a return address and then your program might crash. You get a segmentation fault if you overwrite it with garbage. You very carefully overwrite it with some address where your attack code happens to be, then you might actually do something more interesting. So what is wrong stack usage? What happens? Well, in this example, it was in 2013 that Toyota was convicted or got a very big fine because they had a bunch of programming errors that led a Toyota car, I think it was instead of just stopping when you let go of the accelerator, the pedal would, or the computer that controls the engine would go full throttle, and the car would accelerate until you hit into something, and that actually led to the death of one of the people one of the persons in the car. So they investigated this engine control module thing, and they found a bunch of big issues with regards to this kind of software. So they did not have copies of variables. So if you would override one of them, then it would just happily use that value instead of if you would keep 2 copies and make sure that you each time update and read both of them and check if they are still the same, then you could detect that you've accidentally garbled that value and then shut down the engine, for example. They also did not have this for other types of logic, and then they had a problem where they analyzed their software beforehand, and they claimed that at most we can use 41% of all the memory, so we should be very fine. but then it turned out that they were using a lot more memory because they ignored all of these assembly functions, and they were using recursion, which also often quickly increases the amount of stack that you use, and is actually forbidden by these motor industries software reliability associations guidelines. So they were making a big mess in many, many directions. And unfortunately, someone died in this case. And they also found all of this other stuff. And you might think that the race condition in a car is very funny, but it might not be the best thing to have in your engine control unit. Another limitation of how the stack, that is a result of how the stack works, is an example of that is shown in this piece of code. So we have this table here that is some amount of length. We initialize it with some nice value. Oh yeah, it's a multiplication table. And then we return this table. And we are returning this int pointer because, again, an integer array is the same as an int pointer, more or less. So what happens when we call this function? Well, we're returning the address of this stack variable. And if you remember what happened with the stack of a function, the stack frame of a function after we return from it, well, it's gone. Once the function returns, you move up the stack pointer again, and then the value that you assigned disappears. So then you're now pointing into data that is owned probably by another function. So that was undefined behavior. Another limitation that you have is size. If you would try to make the table of, I don't know, 2 to the power of 10, 2 to the power of 100, then you might quickly run out of space again. There was someone who asked what a race condition was. A race condition is when you have two different processes and that the order in which they complete might be a bug. So that you get these tasks depending on in which way they get scheduled, because multi-threading is not perfect. It's mostly just pretending that you're actually doing stuff at the same time. Might cause it to complete at different times depending on how the circumstances are. This is called a race condition. If you Google for race condition programming, then you might quickly find more examples. Often you will see that, for example, if you have two threads that print stuff, that they print things out of order, that kind of thing might happen. And yeah, it's not entirely clear to me what was the problem here for this Toyota car, but it's typically not something that you want to have. So that is the stack. Then we'll go into the heap. Unless there are no questions on the stack, 1, 2, 3, 4, 5, then I will go on with the heap. So the heap is more like a big piece of scrap paper. We can get a piece from it, and then we own it, and we can write there whatever we want, and we can also pass it through to other people, like how you would cheat on an exam. So this piece of scrap paper is a specific piece of memory, and it's guaranteed to be continuous. So there's no issue if you go outside of a page size or something. You can just ask for a terabyte of heap space if you want, and you can write from the start of it all the way to the end of it. And you get this through a pointer, because what else? Because it's on the heap and not on the stack, it'll only be cleaned up when you ask it to. So this is space that you can pass around to other functions. And everyone who knows this pointer, who knows the address of the start of this big piece of heap space, can read it, can write it, can do whatever. So how do we get such a nice page of paper? So malloc is the function that you call if you want to allocate space on the heap. You call it with the number of bytes that you need, and then well, you need to put this thing at the top of your file, and then size d is a thing that we've seen before that is used to indicate sizes. What you get as a result is a void pointer. A void pointer is a special type of pointer that can be cast to any other type of pointer. Void just means we haven't decided for you what type this is. Figure it out yourself and just cast it to a uint8t pointer or an int pointer, or do whatever you want pointer. Allocating space may fail, and there can be many reasons for this. One of them is that you're just out of memory, or the computer is not feeling like it, or whatever. Whenever this fails, the operating system is refusing to give you more memory, then malloc will return null. A null is not a 0, but it's a special empty pointer thing. In C, void pointer you can just cast to anything. In C++, you need to be slightly more careful because you need to do it explicitly there, but it's more or less the same. In this example, you see that we want 10,000 integers. So we take 10,000 and then size of int, because we need to size in bytes. And then we get this int x pointer to this space on the heap somewhere. Null is guaranteed to not point to a valid address. So null is defined to do this. The way this is typically implemented means that null is also the value 0, because 0 is not a valid address either. But that is not guaranteed to be the case. So don't assume it is 0. Then there's this thing that if you take an address that is not pointing to a valid piece of memory, then dereferencing it obviously does not make sense. You cannot go to this is not a valid place and then see what is there, because there will not be nothing, because there is no such place. So dereferencing a null pointer, like in this line, or assigning the value null to a pointer. No, this is fine. You can assign a value null to a pointer, but then checking what is there is undefined behavior. So again, null is not the same as 0, but for all intents and purposes, it is 0. For example, it's also required to evaluate to false. So again, so one of these things that pushes it in practice to be the same as 0. These two lines are the same. If x equals null, then x is a null pointer, or you could just do not x, then it is a invalid pointer. You always need to make sure that you check for this malloc failure, even though it might never happen, because if malloc returns null, you will start dereferencing this pointer table, and then this will break. It's undefined behavior. Typically, you will just crash the program, and then you are unhappy, but there might also be security issues that happen. So how you would typically do this is that you do the malloc, then check if table equals null. I almost said 0, very wrong of me. Remind yourself that you can leave out the curly brackets if you only have one line in your if. Also for for example. I tried to edit these things back in with curly brackets, but I've missed this one. And then one of the things you could do is call the exit function with some nice high value, for example, to indicate that it's a null error. But it's so unlikely to happen that error correcting for it is usually not what you want. You'll just terminate the program because it's not useful to continue. And again, you could use not table here instead of the equals null. The important thing with malloc memory, with heap memory, is that you need to make sure that you're giving it back to the operating system after you're done with it. There is no way in which C will free it for you unless the program terminates, but then it's still bad form to not have freed it before. Why is that the case? In Java, you don't need to do this, for example, and that is because in Java, there's a piece of software running in the background that's keeping track of all the copies that you make. And then there's also special bookkeeping, so that all of the pieces of RAM on the memory are also kept track of who owns these pieces of memory, and are they done with them already. This is called a garbage collector, and this is also often why, for example, Eclipse or NetBeans or something sometimes hangs for a little bit, because the garbage collector kicks in, locks the entire thing, and is trying to check all of the memory. Okay, can I garbage collect this value? In C, you need to do that yourself. So you need to make sure that you release this memory with free, which means you don't need a garbage collector, you don't need this kind of software running in the background, but you do need to make sure that you free it, and because otherwise this memory will be lost. How you would typically use this? Well, you have a malloc of some memory, then you check if it's null, you use it for a little while, and when you're done with it, you call free x to free up this memory again. And this does not need to be in the same function. It can be that you malloc some memory in a function over here, and then you use it in some other functions, and then it's you free it sometime later at the end of your program, for example, or somewhere else. If you don't free malloc memory, so don't free heap memory, you call this a memory leak, because you're leaking all over the floor with your memory usage. And for a program that runs for 3 seconds and doesn't use as much space, this is not typically a problem, but you might, for example, imagine a web server that's serving web pages all day, every day, for weeks. This process is running, and imagine it leaks 10 bytes every time a page is requested. After a few weeks, you'll see, depending on how many page requests you get, you'll see that it will start be using a gigabyte of RAM or even more, or it will even crash your program because at some point you just cannot malloc more memory anymore. So memory leaks can be very serious bugs, even though when you just test something for a few minutes, they might never appear to you because it seems like the program is running fine. And indeed it is running fine, as long as you have more memory in your computer to just continue leaking. How does free know how many bytes to free from the heap? That is a very good question, and we'll get to that. Yeah, memory leaks can be super annoying to debug. Sometimes you need to expand or shrink the amount of space that is malloced. There's this function called realloc. You give it a pointer and then a new size. You need to make sure that I think you also need to make sure that you check if this is a null pointer, but check the manual. If you give it a larger size, this space is added at the end or taken away from the end. And again, because heap memory is guaranteed to be contiguous, you can just continue writing as if it was always that size. Yeah, it might also contain null. And tricky here is that if it is null, the previously allocated memory is not freed. So then you need to realize, okay, so I still have this piece of memory that's heap allocated, and I need to make sure that I also give that away again before I go further. Although if you just exit, then just call exit and don't worry about it. Yeah, here Erik Paul once wrote this code and he decided to free it. It is very nice of him, but yeah, if you're just going to terminate, just terminate. Calloc is a special variant of malloc. And this variant, the difference here is that it will pre-initialize the memory that you're getting. It also has a slightly different way of calling it. You can specify how many items you want and what the size of all of these items is supposed to be. So what you would do is, for example, if you want 1,000 ints, is that you would do 1,000 of size int. With malloc, we needed to do multiplication here. Very important. We'll see why this is an important difference. And with calloc, you get all of this memory space initialized to 0 for you. And it will also make sure that this memory is available. Malloc is sometimes lazy. So the difference between this with a multiplication and this with a comma is that the result of this computation might actually overflow. This computation, if you multiply, if I want int max times 4 bytes integers, then this will be larger than the size of an int, or whatever the maximum for size t should be. And if it overflows, because it is an unsigned value, you will go back to 0 and compute it modulo the size of your type. You will often get much less memory than you were expecting. But then if you're trying to access the n lms minus 1 element, that will not be there because you actually allocated much less. So in that sense, calloc here is a lot safer to use. Malloc is lazy, so it will, the Linux kernel, the operating system, will just give you the memory, assuming that it can figure out how to give you that memory when it comes to it. This is how you could, for example, try to malloc a terabyte, and there are programs that do that, and because they implement their own memory management, they figure, okay, I will never use more than a terabyte, so I will then just ask for a terabyte and then do my own memory management in my own process. There it is very useful that it is lazy in this way, but then if you later try to access, but this is really if you use huge amounts of memory, then it might still crash. Calloc will give you memory that is actually backed by pieces of hardware. So then if you use calloc, you will get guaranteed amounts of memory. But then, because it's also initialized, it will also slow you down, perhaps. Remember free? Indeed, how does free know how much memory belongs to the pointer? Well, you need to keep track of that somehow. So the place to put that would obviously be the heap, because it's outside of a specific function. And the one way you might do that is to create a table of all of the addresses that you have and how large all of they are. Then you could look up in the table, free that space, and then carry on. A neater trick is to take the pointer that you have, or take the size that you have, add to that the size of a pointer. Then you have a piece of memory that is, in this case, 4,000, because an int is 4 bytes times 1,000, plus 8, because a size t is 8 bytes. So then you have 4,008 bytes. You write the size of the thing first, then you do plus 8, and then you return that value to as the result of malloc. Then you get here the int star p points to actually this buffer 8 bytes in. And then what free does, it simply does minus size of size t, reads how many bytes it is, and then frees the entire space. It's a very neat trick. It's easy to see that it works and how this works, and it is actually how this is implemented in my understanding. We've abused it in an exercise before. Free is tricky though, because dereferencing a pointer that is freed is invalid behavior, which also means that if you free something again, is invalid. This is called a double free, and this is called a use after free. And if you look in, there's these lists on the internet of types of bugs that have been found, CWEs, for common weakness enumeration. And if you look for these types of bugs, then you might still often find a double free or use after free in the description of certain issues. And indeed, people apparently manage to use this type of behavior to hack programs. And the annoying bit here is that if you make a copy of X somewhere and give it to different functions, and then it's very hard to reconcile which of those two functions is supposed to take care of freeing the memory in the end. That can be very messy. And accessing memory is invalid, as in it is undefined behavior. A valid program would not access a freed pointer. If you lose a pointer to a location, then you're also in trouble, because then you're leaking this, because you cannot free it anymore. So then you're also in a bit of pain. So when you're writing software that assumes or uses the heap to put stuff away, then you also need to very carefully consider, okay, how am I making sure that this is being cleaned up later? Then there were these two segments that we talked about last week already. But to summarize, we first have the stack. Stack starts at the top and grows downwards. And actually, the command line arguments are also on the stack. Then there's the heap, and that is somewhere in the middle. But then there's also these BSS data and code segments, and they are from the start. So heap indeed is what we call dynamic memory, because you can dynamically size it and move it around and do stuff like that. Then there's the data segment, and that is where we put global and static uninitialized variables and the global and static initialized variables. So these two are called, also sometimes referred to together as the data segment, because that is where you store data. But some data are stored in the BSS part of it, and some parts are in the .data part of it. And the reason for that is that these have a value and these only have a size, because they're not initialized yet. There's also this piece of thing called text, which contains code. Typically, it's marked as read-only, and that is where the executable bytes of your program are really in. That is where it says add 3, jump there, if the compare this, if flag is 0, do this, all sorts of those assembly instructions, but then as bytes are there in the code segments. Some constants might also appear in that piece of your program. So then we have these global variables. You've probably seen them before in examples of poor programming. Often using of global variables is a very bad practice. But you have the typical initialized versions and the uninitialized example here. We have n and s that will be in data. Typically, s star will be a pointer also to somewhere in the code segment, probably, because this is a constant. And then this uninitialized value will be in .bss, and that will be initialized to 0. And why is that? Otherwise, you might run into problems when you when you execute your program and there's still stuff left there by a previous program, you might have trouble. So the BSS section is typically initialized to 0, but some platforms allow you to opt into not reinitializing it. But that is typically for stuff like microcontrollers where you know everything that is running there. Because you wrote all of the code that is running on there, and there's not really an operating system there, and you're doing all of the management yourself, etc. Then there's static variables, which is a special type of a variable that is local in the sense that it is defined within the scope of this function f, and you cannot access it from outside of the function f. But it keeps its value across calls, as if it was a global variable. And indeed, how you could get the same behavior is just moving this thing out of it, prefixing it with the name of f or something like that, and then doing the same thing again. If f was not declared static, then you would do int x equals 0 each time you call function f, and then increase it afterwards, so this will print 0 every time. But because it's static, it will print 0, 1, 2, 3, etc. Again, yeah, would get the same behavior if x was a global variable, but then the semantics are slightly different because other functions could in principle still access it. So wrapping this up, we have the stack, we have the heap, and we have the data segment. So the data segment exists throughout the entire execution of program because it has global stuff, it has local variables that are static, and that type of information is being kept track of throughout the entire execution. Then there's the stack, which is managed completely automatically. It only exists during a function call, and you can only pass variables down the stack and never up the stack. And if you are not careful and write a function like I did, then you could overflow the stack. Then there is the heap, which is completely managed by the programmer. You need to manually request that amount of space with malloc. You could even get your request denied and then need to figure out what needs to happen then. Space on the heap needs to be given back to the operating system by free, and you have all of these issues of memory leaks and double free, etc. because again, it's not managed by the computer, and humans are a lot more error prone. How can we read the stack though? Remember printf? It writes the output under the control of a format string that specifies how subsequent arguments are converted for output. That's only specified that you have this format string thing, and after that there can come any number of parameters. So what does this program do? This is demo time again. Where do I? There we go. So I need to make a small copy here. Oh my god, what happened? There we go. That is the other example. I could also compile this with all of the warnings. And it really only complains about this unused parameter argc. And let that be the part of the program that we don't really care about. So I print F1, hello, I shouldn't forget to check my microphone. That all works fine. Let me quickly add a new line. Oh no, wait, that's not the problem actually. But what does this program do wrong? It should have been %s and then the arguments. So how can we make this program misbehave? Remember that printf was supposed to print the output under the control of a format string that specifies how subsequent arguments are converted for output. Okay, so what happens if we start print1, printf1, if you start to give this thing a format string? That is an interesting bit of memory that has just appeared. So what is happening here is that it will just start reading it as a format string and start printing the second argument of printf, even if that argument is not there. This happens because printf is just dumb and will just always, okay, %x, then I take where was this argument supposed to be, read there, and then just print it. So this is called a format string attack. It's been known since 1989 that you can use this to read data, like we just did. The first attack that broke something, so people actually managed to write something and break software with it, is from 1999. So it took them 10 years to figure that out. And remember that even reading data was invented a small 17 years after they wrote C and figured out how printf works in the first place. Printf will allow you to read data from the stack, but not only the stack. If you do it in a smart way, you can also use it to read data from the heap. It should be super easy to spot, because if there's no quotes symbol after the printf starts, it's already suspicious. But for weird reasons, we need to specify this compiler flag, because of course, why would you want to turn this on by default? I have no scenarios where there should ever not come one of these after printf, so it should be the most trivial thing to debug. But still, compilers will only complain about this, or GCC at least will first need to be told, please tell me about this explicitly, and even turn on the =2, so the please complain about this super hard version of this warning before it will tell you you're making a big mistake. Clang, which is another compiler, will complain about this by default. And I forgot to switch to my slides again. I am an idiot. This stuff is hard, you know. Reading data since 89, 99, etc. If there is no thing after printf, it's suspicious. If you want compiler warnings in GCC, you need this flag. And the =2 means please warn about this a bit harder than usual, even, because why you want to do this by default. Clang, another compiler, Clang, will complain about this. It says here, format string is not a string literal, potentially insecure, format security. And that is the type of thing that you would want to see. Again, if you call a function, you will first put the return address on the stack, then the frame pointer, and then there will be 6 arguments in registers, and then the remaining ones are on the stack. and then you jump to the address of the function that you're calling. The address are in registers because that saves a lot of time. So what do we see actually? If we run printf%p, we will print the value of the second register that would contain an argument, because the format string itself is the first register that contains an argument. So the argv thing is the first value that we're seeing, and then this is the value that was in the second register that would contain an argument. And we can use this special syntax to print the seventh value. Oh, I should use single quotes now, because otherwise my shell will start to interpret this. And then you will see that we will start reading up the stack. And this is in fact looks like a heap address. I'm not sure where this is coming from. Might actually be code. But we can see that if we start printing a lot of %p's, actually let me automate this a little bit. %p times 50. Oh. Then you'll start seeing a lot of values being printed up the stack. We can use this to debug programs. So if we take the following example program, we have this function doPrint. We call it with the first argument of the program, and we have this super secret variable dead code cafe food. And if we start doing printf with this thing to print 14%p's and then a space, you'll see that some address. So this is the second argument in a register, the third argument in a register, the fourth argument in a register, the fifth argument in a register, the sixth argument in a register, and then the first value on the stack behind you. Then another value on the stack, another value on the stack, the some address, another value on the stack, another value on the stack, etc. And hey, this is the value that we know was in the memory here. This thing is most likely actually the return address of the function. And why is that? Well, we were somewhere here with executing, and then we just started printing functions up, printing these values up the stack, 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 and then at some point we found the return address. And we can actually see that this is the case. So I also have here printf.c, and I can make printf please force this printf. You'll see that this thing is indeed vulnerable. But let's just run this in a debugger now. Break do print. Oh, I am a printf break. Oh, so we have the printf.c function here. I've compiled it with debugging symbols, and I've now loaded it in a debugger. We're going to break on the doPrint function. Break main and layout source. And then we're going to do run and start with hello world. We'll see that we've now stopped execution at this function. And then we're going to do a step. And do a step into the thing, and then we can continue and then complete it, and then we'll see that it's done again. I can also use this debugger to run and then with a bunch of %b's 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. That should be enough. Yeah, I would like to start from the beginning again. I can do print argv1, and you'll see that there is the string that we are trying to print. We'll step into, S is short for step into the printf function, and then I can do info locals, no local variables, info args, and you see that string is again this %p string. And then we will run this printf command. How can I make sure? You also see here in the output that this is where we're currently with executing, which is already a good sign that the address that we saw in the slides was actually in the code region, because this indicates the program counter. But what I can also do is do info frame. And there it will tell you information about the stack frame of this function. And it says here that the register that is the instruction pointer is pointing at this address. That is also indeed where we are currently with execution. But the saved return address is this value. You can see that it's apparently moved a little bit since I made the slides. If I were now to say I want to print this next, where is my output, please? How do I turn this off again? Okay. I should have seen some output appear. Oh well, we should have seen that we saw this address appear. So that allowed us to verify that it indeed was printing the return address, but it is slightly messy to do this demo and fix it again. The questions are now, what are these other values? So one of the addresses that we might have seen is the pointer to argv1 and the other values. A bunch of these registers are also just set to garbage, because before actually the main function is called, there's also a lot of other code that is being run to start up your program. And this value, yeah, that is a very good question where that might be pointing to. It might just be some. This is probably the return address after where the main function is going to be returning to. It's a bit hard to tell that what exactly all of these values are without going into all of the debugging. But remember that not all of them always make sense, because there's also code being run before your program starts. These registers are not zero from the start of your program, and there's also a lot of things that the compiler is doing. What you might also be seeing somewhere is a canary value, and that is that the compiler tries to insert some values in certain places that it will check later to make sure that you're not overwriting the stack. We will be turning off that feature when you're attacking something, and the slides will explain how to do that. But yeah, there's a lot of things on the stack. it's not possible to always assume that the first heap address is the return address. And indeed, this is not even a heap address. This is just where the code happened to be. And since the code segment is just before where the code and the data segments, they're probably not so big and they're just before where the heap starts, they sometimes look a bit like heap addresses. There's also the part where it will differ with what compiler you compile the source code sometimes, if it will put things in slightly different places for reasons of certain security things that it's doing. How you identify that if something is the return address is often just trial and error. If you have a debugger, you can use the debugger to figure it out, obviously, but then you might not be using Printf in the first place. If you are using Printf, then learning that something is a candidate for the return address that you want to attack is just overwrite it, see what happens. If you overwrite it with maybe you add a bunch of values, can you skip a line of code? Or can you insert the address of a another piece of code and then execute another function? There's things you can do there. Trial and error is often part of the name of the game, though. There are some extra content here that have some nice examples of many ways in which you can break things. I will be skipping them for time because of the issues at the start of this lecture. To leave these exercises to you because I think you can figure them out without me. And then what remains for me is to talk about two tools that can help you debug the memory problems that we talked about at the start of this lecture. So Valgrind is a tool that people developed only a few years ago. And what it does is it tries to help you find all of these memory bugs, specifically with heap memory problems. And what it does is it runs your code in a sort of a virtual machine where it does a lot more intense memory management than what you typically get. It will, on every memory access, it will check, okay, is this within the memory? Is this not outside of the memory? Is this memory that there are more references to? Has this memory been freed already? And do all sorts of those checks to make sure that you're doing things in a valid way. This makes running your code a lot slower, which is why you don't use that in production, but it will allow you to find memory leaks because it will keep track of all of the malloc pieces of memory and then keep track of if something is freed or if it's being freed again, or if it's being read after it's being freed, or if you have a branch. So if you have if something and then an initialized piece of memory, then that's also undefined behavior, etc. Valgrind can really help debug a lot of problems. It has also a bunch of specific tools built in that use this virtual machine structure to do other debugging and optimizing of code. A cache grind and call grind can be used to figure out what pieces of code are being used the most, for example, or using the CPU caches in certain ways to allow you to really optimize code, but you don't really have to worry about that. And you also don't really have to worry about Valgrind, but if you write C code, you might find that it is helpful. Valgrind is a dynamic analyzer. A dynamic analyzer is something that runs at runtime. A static analyzer takes your code and then does some analysis without running it. And the difference between the two is that a dynamic analyzer has no guarantee of branch coverage. So if you always take the same branch of an if, and only very rarely the other case, it could happen that Valgrind never catches that you dare do something that is not okay. A static analyzer would have caught that, but then you need that's not always possible to decide such problems. An example of a static analyzer is actually the type checker that is built into the C compiler. That's a type of analysis, that's static analysis. You look at the source code and decide things based on that. With the dynamic analysis, you instrument a running program and see what's happening. So good practice with Valgrind would, for example, be running your code in Valgrind before you submit it, or you publish it to a paper, or upload it as the next Google Chrome release, and then you make sure that it reports no errors. An even more recent feature of certain compilers is that they allow you to link in a special library called libasn for address sanitizer, libaddress And I think Google partially helps with the developing of that project. And you can use this specific special compiler flag to also add in the types of checks that Valgrind is doing. And then your binary will be really be checking this type of stuff at runtime. And then whenever it finds bad behavior, it can terminate and tell you exactly, okay, I was at this point in your program when I accessed this piece of memory that was being allocated by that piece of code. It also has a bunch of other sanitizers, like the undefined behavior sanitizer and the memory sanitizer and the leak sanitizer, the thread sanitizer. They're not always easy to use or helpful by themselves, but fsanitize equals address is often useful, and you can also add comma undefined. Although, again, these things do slow down your program by a little bit. And that was it for me. The assignment of this week is due of, the assignment of a bunch of weeks ago is due tomorrow. There will be a new assignment that's already been put online, and there you might already have a look at for the lecture tomorrow, for the tutorial tomorrow. The student assistance will be available as usual tomorrow, and I hope that this second iteration of going over memory cleared up the mess I made little bit at the end of the last lecture. I really do apologize for the insane mess that we had at the start. I had my phone was on the charger in the other room. I'd obviously turned off the sound on my laptop because that was interfering with this recording, and then I'd hidden the chat behind my slides, and that was a really stupid mistake. And I again do apologize. Fortunately, we're not very much overdue. If I went through something with sound a little bit too quickly, please let me know so I can maybe figure out how to support my description in these slides, either with extra video or by linking to extra resources. But I hope that it will be able to explain itself. Next week we will continue with buffers and with buffer overflows. So then we really get into the exciting part of the hacking in C. What we will specifically start doing is using the stuff that we learned through the technique that I showed you on this slide to start to manipulate this address. And you might already be able to figure out how you can do that by just taking a buffer and then overflowing it. But there's also a way to do that with Printf, of all things. Yes, you can use Printf to write to places. Why did they invent this? I have no clue, but it's there. With that, a bit of a teaser towards next week, I think it's time for me to stop talking and figure out how to next time make sure that I first check the microphone. Thanks for your patience with the start, and yeah, again, I feel really silly. I will be around on Discord a little bit tomorrow, probably during the thing, during the tutorial, and otherwise you know where to reach me through email, GitHub pull requests, the feedback channel. I think there are plenty of ways how to reach me. Yeah, and then I will see you again for the next lecture next week. Shall we start then at 30 instead of at 45? That might be a little bit more in tune with your schedule. I will also confirm that with a follow-up announcement on Brightspace, probably Monday morning. Okay. See you around.